So today, I will not continue yesterday's talk, which was actually self-contained. Yesterday was an applications, and today I'll tell you the background story, which led to a calculation that maybe we'll recognize at the very end of the quantum cohomology of a GIT quotient in that examples in terms of something having to do with the loop group. And the story is quite old. I've put some references here because there is no self-contained complete account. The only written thing was limited to 15 pages. So a lot of the material is in old lectures given over time. If you think 2011 is old, I'll point out that in some form I've been thinking about this question of how one really gauges two-dimensional field theories, probably for 25 years now. And I think I almost have it right, but so close. So some key antecedents in the literature, I won't have time to explain much, is the Olive-Montonen duality, which really is electromagnetic duality in supersymmetric theories that goes back quite some time. And that was picked up and developed by Kapustin-Witten and then Gaiotto and Witten in connection with Langland's duality. So the original Olive-Montonen thing, I believe, had only abelian groups. So they noticed that Langland's duality was a correct thing for when you move to non-abelian groups, and that it was a four-dimensional duality statement. And another, I think, key or winning idea is due to Kapustin-Rozansky and Saulina. And Kapustin and Rozansky wrote a couple of papers about it in, I think, 2010-ish or so, 2011. And I will only extract one idea from there, which I think, and I confess I've only seen lectures on it. I haven't read the papers because there's one idea there that's so far ahead of everything else that really just taking that away and working with it will give you what we want to know. So the key remark, which I touched upon that yesterday when we discussed the difference between A models and B models, quantum mechanics and quantum field theories, and I mentioned in 2 dimensions somehow group actions on categories are essentially derived, whereas topological group actions are rigid, much more like group actions on vector space 1 dimension down. So one key distinction you see that when groups act on vector spaces, sometimes there are no invariant vectors. You get 0 as a space of invariants, and that's why you can construct projectors. When groups act on categories, there's essentially always an invariant category. It would even be much bigger than the original. So you're not constructing projectors from that. However, when you have a topological group acting on a category and the group is connected, and the group acts via its topology, meaning homotopically the action doesn't contain information. In first approximation, that's like a homomorphism of the loop group of G to the Hochschild cohomology of the category. So the chain complex of a loop. The topological homomorphism like from omega to the Hochschild complex of the category. And that's a lot more like a group action vector space. And in fact, you can then specialize and extract. So as you said, I think maybe better. Why is it not? It's you get an E2 homomorphism from the homology of omega G to HH star of C, and this is certainly E2 map, which means you can fiber the category over spec of this, which is a vector space, so it has fibers. So that's I think what explains the switch between A and B behavior for gauging in 1 and 2 dimensions. So let me try to give the executive summary, I think, first. It didn't fit on 1 page, I'm afraid. So I have 2 pages. So the executive summary is a doubly the story is a doubly categorified Fourier transform. And maybe to connect for people who know literature, what's the connection with this? This is a 4-dimensional story duality. What I'm describing is a 3-dimensional duality story, and it lives on the boundary of 4-dimensional EM duality. That's what boundary theory is for. So let's look at the abelian case. And in some cases, it's formal linear algebra. So we take a torus, which is a Lie algebra mod lattice, mod pi1, and the dual torus being dualized. And we have three layers of Fourier transform. So first of all, functions on pi correspond to functions on the Pontryagin dual group. The kernel, it comes from the bicharacter from pi cross T check to S1. These guys are, of course, the characters of T check. Oh, that's a pi, sorry. This is a pi. So the once categorified story has coherent sheaves over the stack B pi corresponding to coherent sheaves on the dual complex torus, if you like. And that comes from categorifying the kernel. This B pi, if you realize topologically as the torus T, that would be just a Poincare bundle. And what it says here, the categories with pi action correspond to, sorry, sheaves with pi, vector bundles with pi action correspond to, well, modules over the ring of functions on the dual torus. So it's saying nothing at this stage. And one step down, sheaves of categories over the double delooping of pi correspond to sheaves of category over the dual torus. And there is, again, a kernel, which is a gerb over the product B2 pi. Bi-gerb, so to speak, bilinear gerb over B2 pi times the torus. And the connection with topological actions, B2 pi, can also be realized as B, not of T, but of T modded with the Lie algebra modded out. Mod out here the Lie algebra, get a B pi, mod out, take a B again, you get B2 pi. So categories on B2 pi are a model for categories with a T action that trivialize the action of the Lie algebra. And that's the definition of a topological T action. So for an example of this, if you really ask, what are topological T actions on vector, you get exactly points in TC check, and that's maybe a better way to say that is H2 of BT with C star coefficient, which characterizes central extension, characterize actions on the category vector. And that's it. This is closely related, I should say, to a notion that's been used a lot in geometric representation theory, or people use action of the tensor convolution category of D modules, or some people like to write the Durham stack that's actually closer to obviously of G, which is just G modulo the formal group. It's normal subgroup, that is a group stack, and it's essentially a Durham cohomology of G. So these two are formally equivalent, and they're closely related to this notion of topological action. In the case of abelian groups for tori, the distinction is not gigantic. It's just being able to exponentiate this Lie algebra action here. So exponentiating the trivialization of the action, so to speak. So there's a difference in the flat connection and its monodromy. So on one hand, yes, you have to be able to exponentiate. On the second hand, you screwed up the algebraic structure. But if you're generous enough, I think you can approximate things on one theory with the other. In the non-abelian case, something more substantial happens, and it's explained by all the results of constants on Whittaker modules. I probably won't have time to explain, but the cartoon statement that goes with this here, the categories topological T action, the sheaves of categories of the dual torus, is that categories are an action of D modules on these double coset stacks and twisted by chi, left and right, correspond to categories over the dual Whittaker stack, well, Langland's dual group, again with chi twist. I probably have to explain that. And chi is a regular Whittaker character of T. So I think this is somehow a substantial difference between the D module side and the topological side now. Somehow this invoking this Whittaker character somehow converts, roughly speaking, D modules thing to integrable D modules in a very loose way. And maybe for people who know, I can say that Constant constructed universal Whittaker module and shows that it's fiber of a center of universal enveloping algebra with simple fibers. So the category you build from that is equivalent to the category of modules over the center. And that is also a category of modules over the homology of the base loop space. So miraculously, somehow, we're replacing the Lie algebra with a Lie homotopy type of G in that, by this move. I not claim I have complete control here. And anyway, this side isn't quite right because, at least because of the torus is still a little wrong, but controllably. But that's what the statement wants to be. The precise statement, in fact, would be exactly right on this side, and here, well, you have to take it with a grain of salt. So now the second part of the executive summary is that, well, unfortunately, it's not as simple as that. So the real story requires, we talked about categories over something or something else, like a dual torus or some stack or a classifying stack. But what we really need are sheaves of curved categories. And in practice, that requires Z2 gradings. We won't find anything interesting if we insist on Z gradings, usually. And once we have a curving in the business, I mean, that's often a function on the base. So now we can talk about functions to get to a decategorified statement. But the asymptotic solution to the quantum differential equations are the Moret-Cartan curvings of the respective categories on the two sides of the Fourier transforms. They're the thing which tell you how you deform your sheaf of categories from something constant. And they're in Legendre duality, and that's simply the statement that graphs are Lagrangian inside the symplectic manifold that relates the two sides. And I'd like to say that the genuine solutions are in Fourier duality. That's be similar to a theorem of Claude Sabat for D modules, saying that for when you switch P and Q in a non-commutative ring, under certain conditions, the solutions of the respective D modules are in Fourier duality. Here it's a little trickier because one side is periodicized. The space will be a cotangent bundle of a torus, not a cotangent bundle. And actually, in K-theory, it's a product of two tori, doubly periodicized. Now, we know, we've heard from Hiroshi, that on one side, a genuine solution, I think based on work of Kunko Pandaripande, I think, can be described in terms of a gamma function and a J function. I like to call that Gromov-Witten gamma function because it is. So that's a genuine solution. What comes in here seems to be it's the Stirling asymptotics of that. It is a solution to viewing the Lagrangian as giving a differential equation, solving that with this kind of like infinitesimal step of the difference equation. So that's the decategorified consequence of Fourier transforms. But actually, this is kind of a theorem, I would say. I don't think it's a conjecture, at least up to here. From here on, I don't think I understand functions well enough to make bold statements. So the space in question, as I said, is a cotangent bundle of the dual torus, which is also the dual torus times the Lie algebra of the original torus. The natural symplectic manifold has a very natural non-commutative deformation. That's where the difference equation comes from. Where did I say that? Right, because if you think of the base, this as the base, which is the more natural base, the fibers are periodicized, so what you have are non-differential operators, but exponentials of differential. But notice also that functions on T are also the cohomology of BT. So again, to leading approximation, we want to say a category is topological action of the group T should be local system of categories over the classifying space BT, which would be the same as model categories over functions on T, or sheaves of all linear categories on the Lie algebra. So already we have a problem here because I've told you that categories topological to action are two different things. On one hand, categories on the dual torus, on the other hand, categories on the Lie algebra, and the two things are really different. So it can't be both. It's got to be one or the other, but then you wouldn't have a Fourier transform. So the answer is really it's neither, it's something bigger than both. And the bigger thing than both is, let's get a grip on time here. The bigger thing than both was postulated or proposed by Karpusny, Rodansky, and Saunina. And I think they started with the observation as a problem with the way we usually think of matrix factorization categories over a, say, complex manifold, holomorphic superpotential. So here are two examples of the problem. The first example is if you have a submanifold of X, then I like to say physicists tell us that, but actually it's not just physicists. I think we know how to restrict the matrix factorization category to a submanifold. You restrict the superpotential first and then compute the matrix factorization category. But for example, if W has no critical points on Y, then the category has supported joint from Y, so any restriction you could define ought to be 0. So this doesn't work. The second one is a calculation that you can do as an exercise. Now, matrix factorization category is always a module category over the functions on the base. It's not categories. And you can compute its Hochschild cohomology by a complex. We saw probably dance talk, or I think in a talk yesterday, from the usual polyvector fields per differential given by contraction or differential of W. And that lives over a Jacobian ring, in fact, of W. But because it was an OX module category, you would also compute the Hochschild cohomology over OX. And now the ring over which you take home is O tensor over O with O, is just O, and suddenly the Hochschild cohomology lives everywhere. And yet the category only lived on the critical points. This is actually an honest calculation. You can use a scaling variable to scale the superpotential to 0, and working in a formal neighborhood of 0, this is a correct calculation in homological algebra. So there's a problem with the picture. And what they propose, that what we think now is a correct picture, is that matrix factorization categories don't localize to the base and micro-localize somewhere, for example, to the cotangent bundle. And then and what we call the matrix factorization category is simply a home between categories supported on the 0 section of the cotangent bundle, just the usual category of derived category of cotangent sheaves, and some other categories supported on the graph of the W. So they should have said here, it lives on. Now, there are various ways to execute this proposal in the case of cotangent bundles, especially if you start assuming C star scaling invariant things, and that then is really just homological algebra. Otherwise, you can assume things are supported in a 0 section. Again, homological algebra gets it. Gets a bit trickier to really put some geometry, make things global. But anyway, what we'll have is not exactly a cotangent bundle, so that wouldn't quite work. But here's how we solve example 1. Where does the restriction of the matrix factorization category live? Well, it lives in the intersection of the graph of dW, the conormal bundle of Y. Okay, put the conormal bundle of Y. Write it. So it's on graph of dW intersect with the star conormal bundle of Y. And that exactly captures the critical points of W restricted to Y. So that gives the right answer. So it solves that problem. And it also solves this, the first problem, because now you're taking home sort of not on the 0 section, but on the manifold where the category is actually supported. So it's not surprising you get Hochschild cohomology of O over itself. You just get O on the graph again. And when you read on the base, when you project, it looks like it lives everywhere. All right. So the precise proposal, which I think is still unsolved in full generality, is that there should be a 2-category associated with an algebraic symplectic manifold, whose object should certainly include sheaves of, well, maybe sheaves of categories, all linear categories with good properties, maybe supported on smooth Lagrangian. And in a neighborhood of a smooth Lagrangian, you should get exactly the 2-category of OL linear categories, I should say locally. They have global deformations. So it's really a micro-localization of the 2-category of module categories. But it depends on the ambient space, the ambient symplectic space. And what I proposed a long time ago is that the correct notion of TQFTs with G action generated by categories, by topological categories, should be the 2-category of associated the total space of the total integrable system for the Langlands dual group. In the case of a torus, is a cotangent bundle PCM. We could call that a Fourier transform conjecture. I think in this case, you have the dual torus and the Lie algebra of the torus. So the answer to the puzzle, well, do they live on the Lie algebra of T or on the dual torus is, well, they don't live either. Live in a bigger space which contains both, and you can localize at your choice of place to read off different things, and two different things you read are Fourier dual to each other. That's it. That's kind of the answer to the puzzle. I had called it a BFM space because it was described topologically by Bezlukavnikov, Finkelberg, and Merkovich, 2005 or 6, I think. But I think meanwhile it's got rebaptized as the Coulomb branch for three-dimensional n equals 4 pure supersymmetric gauge theory. And there was much rejoicing. The lesson is, don't try to compete with physicists for naming things. No. They're in a different league. No, not going to happen. All right, so the only really big conjectural part at the time was the existence of something like this, where everything lived. Actual calculations we know how to do, so they're actually checkable statements, they just didn't have a home. So now there is at least a minimal home for that, but I won't talk about that today because that's, I'll probably spend the rest of the lecture talking about that. It's not that interesting. It's a cheap trick that produces something in which some of the local calculations that KRS wanted can be reproduced, and that's good enough. If all you want is some home where all the calculations live. So instead, I'll give two constructions of how you get two pictures maybe of topologically gauged theories or categories. One of them is directly in this space. I'll say actually very little about that. One which is older has the virtue of being more explicit. So I'll start with that one. So I think I've already discussed that in the executive summary a bit. So two-dimensional DQFTs are generated by categories, and in A-model group actions, the group acts by its topology, and that's the kind of thing we want to make precise. And the too obvious version is we trivialize the action infinitesimally, and then we're acting by the Durham stack of the group, G mod the formal group, you trivialize infinitesimal motion, so it would be like, like asking for infinitesimal movements of G to not show up. So maybe I should write an example of that, of something which is infinitesimally trivialized, but not topologically trivialized. And that explains why people in geometric representation theory use it. I think if you let G act on U of G or U of G modules, maybe on the algebra modules by conjugation, then of course the Lie algebra action is in fact as a commutator, so it's inner. Infinitesimally, it's trivialized, but the action is not topologically trivialized. If you take an actual group element and conjugate the Lie algebra representation, the result is not isomorphic to the original. We cannot exponentiate the trivialization, but I think this shows why, if you're doing representation theory, this is the first, clearly a good notion to start with. But actually it turns out to be good enough to give a concrete model for computing, let's say, the fixed point Fuqua category, if you have a nice presentation of it. So it does give something very good. And the second definition is locally trivialized action. And in the case of a torus, it's easy to give a pretty rigid model of that. You just say re-trivialize the entire Lie algebra action as a group. So you trivialize the group action and lift it to the universal cover. Maybe that's the best way to say it. That gives a rigid interpretation. In general, it's a soft interpretation because you have a contractible cover of G by its path groupoid with fiber omega G. And that's good for something. What this does, in effect, so I'm assuming G is connected. It replaces the group G by the classifying space of its loop space, just as a homotopical. The group in the homotopy category. It leads to a correct starting picture, but it's kind of not rigid enough. You can see why. You could do it for any group G, and then you lost track of the fact that it was a Lie group, let alone a compact Lie group. So something about this is probably not quite right. It isn't. And there is an intermediate model that's helpful where you replace the Lie algebra by the rational complex Lie type of the Lie algebra. So for example, for SL3, instead of having the SL2, so instead of the Lie algebra SL2, you're going to have a Lie algebra of rank 1 in degree -2 from the group. And that's kind of replacing, that still gets you to omega G, but it's slightly more geometric model that can be used. In the case of a torus, we discussed that you don't want to do anything to pi, you don't tensor it with C, so leave pi 1 as it is. That's what rational homotopy tells you to do anyway. All right. So let me give you the first model, which is very rigid and differential. So what's the advantage is it's something you can explicitly write down, and it contains what I call the equivariantized category. It tells you exactly what you need to know to give to define the group trivializable group action, trivialized group action, topological trivial, locally trivialized group. So drawbacks of the model, you need a differential formulation for everything. So a DG category, the action must be given a differential manner. So that doesn't, I mean, usually Fuqua categories don't come that way. So that's the application, then you need to be lucky to be able to implement it. The other drawback, it does not distinguish between the infinitesimally trivialized action, G mod G hat action, topological action. So because of that, it looks a little more complicated than it needs to be. You need to lose a bit of information to get to what you really want to compute. But if you input a good category, your topological trivialized action, and you have a differential presentation, will compute the right thing. And the other thing is, well, the equivariant quantum cohomology has an algebraic structure with respect to shift operators and equivariant parameters, and that's not going to be clear at all. You get sort of transcendental things here instead, like exponentiate integrals of it, for example. So this is based on reinterpreting the Cartan model for equivariant cohomology of a manifold X. Remember, that's take differential forms on X, tensor with the symmetric algebra of G star polynomials on G, take group invariants and add the RAM differential plus a Cartan component for a total Cartan differential, and it squares to 0 on invariance. It doesn't without invariance. It squares to the lead derivative action. But when you take G invariant, it squares to 0. And I remember when I was a grad student, I was wondering, well, can we fix that? He said, you don't have to take invariance. Funny. And actually, yes, but what you get is a curved algebra. So write the same thing, if you like. I put differential forms to have something there, the same differential, but add a superpotential, which is purely quadratic. So it pairs, this is a delta derivative of a delta function on G at 1. This is just a polynomial function on G. So delta function at 1 is in the group ring of G. So I have to take something like distributions on G to have this really sit in as a superpotential. If you exponentiate the superpotential, it's a bit more obvious because you have G acting and the base is G and whatever lives over G. And the superpotential is just the exponential of a superpotential, just the exponential map from the Lie algebra to the group. That's what this value is. This is a curved algebra, as the first exercise to check. The second exercise to check is not obvious, but modules over it form a symmetric monoidal category with respect to pointwise multiplication in the base, and of course the tensor product over the base because of the Hopf structure on G. And that's because even though you have a superpotential, it's bilinear. The convolution allows it to give a multiplication. Now, usually you wouldn't get a tensor structure on the category of curved modules. The superpotentials add, but the addition law is convolution in one factor. And there's a unit object for this tensor structure, which is just putting nothing there, so just sim G star, the unit category there. And the two category of module categories localized at the 0 point is equivalent to the representation theoretic, like trivialized, infinitesimally trivialized G action. So it's actually a Koszul dual of D of G that's happening here. A superpotential is a dual of the commutators, a double dual of a commutator inside G. It's an E2 Koszul dual. All right, so here's a model how you would put a G action in a category. Well, first, you need a group action by automorphism. So infinitesimally, that gives a derivation action. So it should be a Lie map from the Lie algebra of G to 1 cocycles. And then you want the Lie algebra to be trivialized. So you want this map L to extend to an L infinity morphism. This now is in degree -1. From another copy of G into 0 cochains, and this has to be whole thing has to be an infinity map. One easy example that's very common, in fact, is when L is actually 0. Then there's no beta. This guy is commutative. So this class is essentially a superpotential on the space G, which tells you start with the category C at the origin and then spread it out all over the Lie algebra, but deform it by a superpotential. In the Cartan case, this is epsilon, and this is a derivation of degree -1. So yes, it's a 0 cochain, Hawkesbury cochain. So this map doesn't have to be linear. In an interesting case, it will not be. As I say, it could be any function in superpotential. So in the Abelian case, that would be essentially exactly right, but because the group is on Abelian, it's a little funny. The order of the operation doesn't quite allow it to do it, but how do we think of this? Because we're starting with a category with a G action. Now we're building this deformation family. The deformation family is dividing by the odd part of the group. Dividing by an odd group is a deformation. The Chevalier complex of that is even. And that's the base of a deformation. So if the Lie action was 0 and epsilon is always deformation class, now what if it's not 0? And that actually happens if you have a torus action, interestingly enough, in examples. It's certainly a deformation class on the G invariant part of the category. And if you think for a second, that is what you get as you try to restrict what happens. What do you get if you specialize at an adjoint orbit in the base, G mod G? You get you still have the group actions, you get the G fixed point category. So that's an extra layer of complication in general. In practice, it's not, because it's easy to remove that information. If the action was really topologically trivialized, then locally taking G invariance is just tensoring with the representation category. So inside you recover the origin category. That does nothing. And an example you can write, if you write for this for the gauge linear sigma model, then the superpotential is exactly the one you would write. We know from decades ago the trace of psi log psi minus 1. So those are the Stirling asymptotics of the gamma. The second picture is advertised from the beginning, a total realization. And it has some advantages and disadvantages. So the construction is topological, so you don't have to start a differential representation of your category and the action, which helps. And second, it makes a Fourier transform property manifest, because it's exactly the space, in the space where the Fourier transform happens. And the disadvantage is, well, giving that doesn't quite tell you right away what the equivariantized category is, by which I mean the category, this extended category over the adjoint orbit, space of adjoint orbits. That's the deformation. The base of the two spaces is the same, is the space of adjoint orbits in the Lie algebra for the Cartan model and for the realization. And I may not be able to explain that, but the relation between them is sort of a fiber-wise electromagnetic duality. But so they look very different, but they compute the same thing, modulo distinctions I mentioned earlier, right? So they can't quite be equivalent because of it. This one applies to infinitesimally trivialized action, the other one really applies to topological actions. And that's why I actually don't know how to write a global explicit kernel between them that relates them. I can write them the kernel whenever a stabilizer is constant. You can write the explanations on strata in the base. And homological algebra tells you how to glue them, but an explicit formula for the kernel, I haven't found. Anyway, what was it? Right. So the Toda space. So let's recall results going back to this Toda, but also Bezrugavnikov, Mirkovich, Finkelberg, and some of it goes back to Bielawski. First, if you take the G-equivalent homology of the loop group with the Pontryagin product with complex coefficient I didn't write, spec of that is the space we're interested in. I didn't say, but it's a holomorphic symplectic manifold. Algebraic symplectic manifold. It can also be written as the holomorphic symplectic reduction of the cotangent bundle of the Langlands dual group by left and right copies of the maximum important subgroup at the Whittaker characters, so not at zero. So it's like it's a deformation of the cotangent bundle of G check mod n mod n. That's actually maybe it's worth writing like now. A remark. I should have written that. So on the stack, G check mod n have the class. So the bi-character chi gives a class in H1 with coefficients with O. And if you take D of that, actually it will star, I think, and then take the log of that gives you a shift of the cotangent bundle. So vertical shift deformation of T star of G check mod. Okay. You're losing the zero section and lose vertical shift, but it is because it's by D of something, you still have a holomorphic symplectic structure. And miraculously or not, this shift converts this very stacky object. So T star of G check mod n is n check technically gets deforms to the Toda space. Now a class in H1 of something with coefficients in O, well, it's not clear what it does, but the class in H3 of something coefficient with O is part of the E2 Hochschild cohomology of X, which gives you deformations of the category or two category of O model categories of the two category. Why are we in H1, not in H3? Well, because the character has degree 2. So in this space, which was, well, however you write it, the cotangent fibers have degree 2, just like in the curved Cartan complex. The base, the cotangent, yes, the base has degree -2. Linear functions on it have degree 2 for homological reasons. So actually, though it may have looked like this class had the wrong degree to deform the two categories, it has exactly the right degree. But this deformation, just like the curving in a class in H2 of O star for the category of sheaves, doesn't deform the algebra, it loses the algebra object in the category. So you might think that you're approximating the cotangent bundle of something, but actually that shift kind of exactly loses a zero section, moves to infinity somehow, and you're getting a deformation of the category of sheaves of two categories of sheaves of categories over this space. So it's a little more awkward to discuss the Fourier transform in that language, but actually this one is very honest, at least. This does. So that's what, from this perspective, that's what we're trying to, that's one side of the Fourier transform. And because this displacement is entirely shearing the vertical fibers, there are still points, and the points of the stack can still represent points like in the new space. So they quote the fibers over those points. And they correspond to actually flag varieties of G as far as categories of G actions are concerned. So all the flag varieties of G with all the small quantum cohomologies correspond exactly to the points. So that's a feature of this Fourier transform. And the other useful thing about this, somehow that's again a distinction between the algebra representation story and topological story. You can reduce computation to Weyl equivariant torus computation, because this space is a resolution of singularities of the cotangent bundle of the torus, modulo the Weyl action, the total Weyl action, affinized by removing some divisors. So we're trying to do calculus of coherent sheaves here. It's almost the same as equivariant calculus in the cotangent bundle of the torus, unless you're very unlucky and say you had some sheaves that were going to infinity. But in the examples, if you're looking at compact manifolds group action, that cannot happen because the projection to the base must be free and finite. Equivariant quantum cohomology is free of finite rank over the base, so you cannot lose a point, which means in the compact case, you really can reduce to the torus in the bundle. All right, the theorem is that goes with this side is that the support of a quantum cohomology of a compact manifold Hamiltonian action is Lagrangian inside the total space. And more than that, it actually defines a difference and differential equation over the base of the system with values in the quantum cohomology. So it's stronger than just a Lagrangian. If it was singular, it might be a little problematic. But the way you see that is you turn on the circle action compatibly on the quantum cohomology and on the space. That turns on the non-commutative, that deforms the space to a non-commutative space. And we know the circle action here is trivialized in quantum cohomology. So you get, it goes to a deformation quantization module, and that will allow you to set up and solve a differential equation. And the solution to the equation, this differential equation, gives you the equivariantized Fuqua category over X. Meaning if you knew the Fuqua category originally, and you know the quantum cohomology here, you can track how it deforms. And I guess to leading order, you can say, well, just a constant family, but then you have to add Moret-Cartan class obtained by tracking this. So this gives you the Kodaira-Spencer deformation classes as you move along the base. So the downside here, if you want to write out explicitly what you get, you have to solve that equation. Of course, in the Cartan case, you had it as part of the data, but you had to have it in some way. So it was required to be able to write it down. So, and now let's just say, I mentioned last time, there is a careful way to define the invariant Fuqua category. It's not the one given by homotopy theory. It's the global sections of this deformed category over the Toda base, over the adjoint orbits in the Lie algebra. And there can be supported, depending on where Lagrangian lives. Lagrangian could be supported at the intersection with the unit section, and that could be far away from the point 0. And order by order homotopical calculation would only see the point 0. So this space provides the uncompletion you need to compute fixed point categories. So the starting point was a Fuqua category of X, then let's put some information about the group action. You only know something in the neighborhood of this fiber, homology of omega G. And the extra datum, and the quantum cohomology, tells you how to extend that in the entire space, and then you can compute a fixed point category. It's a story. And yeah, I mean, I just mentioned an example that's a bit made up. You could oh, well, actually, no, sorry, it's an example that explains what I mean here. That's actually maybe worth saying. I've lost everybody yet. In the case of so the toy example of the same thing. Let's say you have a base space, smooth base space X and a superpotential. So you can think of it as a deformation family starting at any base point for the category vector, parameterized by a space X, and dW tracks the deformation class. And when you exponentiate that, you get, well, an object in the Kapustin-Rodansky-Saulina 2 category for the cotangent bundle. But now you ask, what's a global thing? What are the global sections of that object over X? That is the matrix factorization category. That's a fixed point, the analog of a fixed point category. So it's a deformation family for the category. It's a global section over the parameter space to give you the fixed point category. And maybe, I think, I will end here. Let's see if anybody has.
So you actually need a fixed point category. Like matrix factorization for the log of W or something?
Log of W.
Like
No.
Like
that.
S1.
Oh, I'm sorry. Yeah, that was a C. I have no idea what kind of C star. Sorry about that. Yes, I didn't want the W. Sorry about that. Yeah. Well, yeah, actually, something I didn't tell you. I didn't tell you how you relate the two pictures, but maybe I'll say one word. That so in this projection, the fibers, even in the non-abelian case, generically are periodicized. And you can ask, well, that's not like what we saw in the case of cotangent bundle, but in the curved Cartan complex, the fibers have the category representations of G in the fibers. So in the case of a torus, that's exactly the lattice of the dual torus. So adding this G fixed point category corresponds to periodicizing the fiber product system. You can do total calculations showing it become the same in both samples. The convolution algebra of distributions or smooth functions, we're going to be generous about that. So let me say what happens maybe in a trivial case. I will, because otherwise maybe it doesn't. What is it? Who knows? So let's take let's take the curved Cartan complex for torus T. So the algebra is T. What is G cross what is that sim T star? Spec of this. And the original W. Well, so G acts trivially in this case. It helps a lot. So it's a disjoint union over characters of T, lambda in home T into S1, of a copy of T, a sheet of T. And on that sheet, W is simply the linear function lambda. So when you have some other, if you add, for example, some category, some other superpotential, and you're computing critical points, well, ordinarily, if you just took the cotangent bundle on the base and compute critical points, you would look for points where dW prime, so other categories, let's see, other category with W prime. So without the group, you could look for dW prime equals 0. But with a group, you have to repeat that on every sheet. So you want dW prime minus W lambda to be 0. So with a group, you're trying to solve for dW prime is lambda for all lambda. So you're not taking the intercept with 0, but you're taking the intercept with periodic sides, and that's the same as folding it into something periodic. So that's what it's actually not rocket science. why the calculation works.